In the last video, we have discussed the concept of potential energy and we have seen the conservation of mechanical energy of a system which is in a conservative force field. So in this example, we are going to apply those concepts for better understanding. Now, what is happening? A bob of mass m is suspended by a light string. Light string, we are saying here, we can consider the string to be massless and the length of this string is L. When the bob is at its lowest point, let's say this is bob and this is string of length L and mass of this bob is m. So when it is at its lowest point, let's say this point is a velocity of v naught has been imparted. So velocity v naught has been imparted. Then it completes a semicircular path and it reaches the top point in a vertical plane. This plane is vertical plane here. Okay, let's move to the next slide with a better diagram and then we are going to continue. So what is happening here? This bob has mass m and speed or velocity of v naught has been imparted. And when it reaches to the topmost point, which is C, the string becomes slack. So there is no tension. So let's go to the next slide here. This is the bob at its lowest point, point A, and then a velocity of v naught has been imparted here, and it continues semicircular path. It comes to C, and then tension in the string becomes 0. So what we are going to find out here? Let's check. First, we have to find out velocity v naught. Then we have to find out speeds at point B and point C. What is the point B here? So this is midway point here. And then we have to find out the ratio of kinetic energy and then comment on the nature of the trajectory of the bob after it reaches at point C. Okay, let's go one by one. So first, uh, here at the lowest point, look, we are going to consider the lowest point here, potential energy to be 0. This is our reference length. But there is kinetic energy. As this bob has velocity of v naught, there is kinetic energy of 1 by 2 v naught square. In the same way, here it has kinetic energy of 1 by 2 m, whatever be the speed here. So let's say this is Vb, so Vb square, and potential energy will be here mg and this height. So L. We have seen this thing in conservative force field. The path of the body is not a matter in its potential energy rise. So this bob is going up to height L, no matter which path it is taking, it will have mgl as potential energy increased, you can say. Now, if we are talking about this point C, the kinetic energy will be 1 by 2 m and whatever be the velocity here, let's say vc square, and potential energy you can guess now, it will be 2 mgl. So we have kinetic energies and potential energies at different levels here, means at point A, point B and point C. So what is the important thing here? The mechanical energy, that is the sum of potential energy plus kinetic energy, should be equal. The mechanical energy at point A should be equal to the mechanical energy at point B, should be equal to the mechanical energy at point C. Okay. Now coming to one more thing here. If a body completes its revolution in circular path, it has, let's say it is going up to here only, a semicircular path. So ultimately its trajectory is a circular. So it has a centripetal force acting towards the center of this circular path. So that centripetal force is mv square divided by r, which is radius, and here r is L. This radius is L. So mv square by L. Let's say at point C, it has a centripetal force of mvc square by L, and this centripetal force is coming from this mg, the gravitational pull, which is pulling it downward. And as there is no tension at point C, it is mentioned in the question here that the string becoming slack only on reaching the topmost point C, that is tension is 0 here. So the only force contributing to the centripetal action is mg. So this mv square, that is vc square, divided by L, that is centripetal force, should be equal to mg here. Now mvc square equals to mgl, and if we are writing 1 by 2 mvc square, this should be 1 by 2 mgl. What I have done here, I have applied Newton's second law of motion here. This centripetal force is due to this mg only, so I have equated mv square by r, which is in general form. Here v is vc and r is L. So mvc square by L, which is centripetal force, and this centripetal force is equal to mg, because this mg is acting as centripetal force at point C. And then we have done some mathematical steps here, and then we have reached half mvc square equals to half mgl. And you know, half mvc square is kinetic energy at point C. So this is 1 by 2 mgl, and kinetic energy and plus potential energy will be the mechanical energy at point C. So if we are going to obtain mechanical energy at point C, this should be potential energy, which is 2 mgl, plus kinetic energy, what we have obtained here, 1 by 2 mgl, and ultimately it will come 5 by, you can add by yourself, 5 by 2 mgl. Now, conservation of mechanical energy, because this all thing is happening in a conservative force field, that is gravitational force field is a conservative force field. So whatever be the mechanical energy at point C, the same mechanical energy will be at point A. Just there will be difference in kinetic energy and potential energy terms, but the total mechanical energy will remain the same. So this E, we can equate E equals to total mechanical energy at point A, which is 0 plus 1 by 2 m v naught square. So 1 by 2 m v naught square. And now we have one thing here, E is nothing but 5 by 2 mgl. So we can write 5 by 2 mgl equals to this much. So 1 by 2 m and 1 by 2 m, these things are on both sides. So we can remove, and then we have, okay, let's move to the next slide after here. 5 by 2 mgl equals to 0 plus, we are leaving 0 here, 1 by 2 v naught square times m. Okay, so this will be 5 times gl equals to v naught square, and then v naught equals to, we are taking under root 5 gl. This expression we had to derive. Look here. So we have to obtain expression for v naught, what we have done already. Now we are going to obtain the speeds at points B and point C as well. Okay, so at point B, look, we have here one key point, and this key point is that the total mechanical energy is 5 by 2 mgl, and now we are going to use it again and again. So let's say at point B, so at point B, the potential energy will be mgl, as we have already seen this thing, and 1 by 2 mvb square, and then we will have this total mechanical energy will be 1 by sorry, 5 by 2 mgl. So this will be okay. Let's do further. Then we can write gl plus 1 by 2 vb square equals to 5 by 2 gl. Now we can multiply 2 on both sides. Then we will have 2gl equals to plus vb square equals to 5gl, and then we can simply write here this will be 3gl. I'm transposing this 2gl on this side, or we are just subtracting 2gl both sides, and then we will have vb equals to under root 3gl. So we got velocity at point B, we got velocity at point C. Sorry, we have to find out velocity at point C now. So at point C, total mechanical energy is the same 5 by 2 mgl, and at point C, kinetic energy will be 1 by 2 mvc square plus potential energy will be 2 mgl, as we have already seen this thing. So we will have 2gl plus 1 by 2 vc square equals to 5 by 2 gl. Now we can multiply 2. So 4 gl equals plus vc square equals to 5 gl. And from here vc square equals to gl, or we can write vc equals to under root gl. Okay. So we have obtained speed at point A, at point B, and at point C. Now, what is the next thing? The ratio of kinetic energies Kb and Kc. So I'm leaving this part to you. You can do one thing. You can do 1 by 2 mvb square divided by 1 by 2 mvc square. You can do it by yourself. Now, comment on the nature of the trajectory. Now, from here, if it is at its highest point here, and if this bob has some velocity vc, it will continue its circular trajectory. And there is a special case. What happens if this string breaks here? So if this string breaks here, this bob is now free, and it is now acting like a projectile body. How? It is like a body projected horizontally in a gravitational field, and then it will move downward like in the opposite way here. So it will move downward like a projectile body. So here, let's say this is Bob, and it has velocity vc, and there is no string here, so it will come down like a projectile. So that's all for this video. In the next video, we are going to discuss about the spring mass system. So we are going to see how the forces are acting there, and what are the energies involved, potential energy, kinetic energy, and we will go through all those things minutely with along with the plot, kinetic energy, potential energy plots and all. Okay, then let's see what are the things. See you in the next video.